So let's go back to our sequence of power and time. And suppose that you are going to shake your hands or shake your electrons and send that wave up and down. Now your job is to make sure that in that wave, you represent those zeros and ones. That symbol, those chips, they have to be there anywhere. The question is, how are you going to represent those zeros and these ones in that wave? There are a few techniques, and if you master those techniques, you're going to be savvy in many other technologies that use radio communication because they are used pretty much everywhere. So, one thing you have to do is to define a tempo, and you can hear my snapping. That's something that you can call the clock, or the tempo, or the speed. That's a speed at which you and the other station are going to decide that you are talking at. So you're going to define times at every snap, and at that time, what you're going to do is to look at your wave and look what happens at your wave at that time. This means, of course, there is a need for a sort of synchronization between stations, but typically that synchronization doesn't need to be very complicated. It's just a basic clocking that can be readjusted as you go, even with a cheap silicone that doesn't have a very good clock. And between each tick, you're going to send a certain number of waves. Those do not matter. What matters, what happens at click time. So one technique, a very simple technique that is used everywhere in Wi-Fi but many others, is called the binary phase shift keying. That looks like a weird name, but what happens is very simple. You send your wave, and then at the point of the click, you're going to look at what happens at the wave. Let's suppose that you are sending a 0. We're going to adopt a convention between me, the sender, and you, the receiver, that if that's still 0 I want to send, well, I'm going to continue my wave as if nothing happened, like this. Because there is no change, nothing happened at the click time, then you know that this is still a 0. And then we're going to agree that if I want to represent a 1 instead, I'm going to do something which is to change dramatically the direction of my wave. So you see in my third area, you see the shadow of my green light. My line was going up, but I'm going to decide that if I want to send a 1 instead of continuing my wave and going up, I'm going to go suddenly down. So if you're the receiver, you notice that my wave was going up and boom, suddenly it goes back down instead of continuing its way. And you know that change means that you're now sending a 1. And we repeat the same logic at every click time, which means in the next one, if my wave was going down, I suddenly go up, well, you mean that again, that means a 1 because you're changing direction. And if in the next one, I continue going down suddenly while I was going up, that's again a 1. And if, of course, I go down as I was going down, like say there is no new change in my wave at the next click, I know that this means 0. So you see, we can adopt this convention to say that every time you want to mean 1, instead of continuing your wave as it was, you just suddenly change its direction the other way. That's called binary phase shift keying. Again, it's used everywhere. You'll find people saying it's called differential BPS key because you look at the difference between 0, which is your reference, and 1, which is the thing that changes. There are a few variations of BPSK, but they are always doing the same. You could decide that 0 is when you change direction. You could decide that if the next one is the same as the previous one, then nothing happens. But if the next one is different, then you change direction. You see you have a few variations of BPSK. What we use at Wi-Fi is the one you saw on that black board. But you see, it's pretty simple. It's pretty simple, but it's also limited, right? Because if you send 1 megabit per second, it's pretty limited. Because if you send 1 bit times 11, and you need 22 megahertz to send all that, sending that speed with the speed of the click means that you can have a speed of up to 1 megabit per second. So that's not too bad. That's 1 million chips per second, but that's not gigantic. So how can we do better and go faster? With the same clicking time, find a way to represent more bits in our waves. That's where QPSK comes into play. And here we say, well, why don't we group bits by 2? Instead of looking at each bit individually, I'm going to take sequences of 2. So I'm taking the same scale, I'm taking the same clicking mechanism, but instead of looking at each bit, I say that each wave, each between click wave, contains 2 bits. For example, I start with 0, 0. And here I'm going to make a slightly different change. For example, I can say, if I want to represent 0, 0, next, I just do what I was doing with BPSK, nothing changes. My wave continues just the way it was. That's 0, 0. But if instead I want to represent something else, for example, 0, 1, here we're going to adopt a little bit more complex rule, a little bit more subtle, but also a little bit more efficient. So you are going to say, for example, if my next sequence is 0, 1, and I was going up, I'm just going to keep on going up, but instead of continuing where I was, I'm going to restart from the bottom of my wave, just like this. So you see, I was going up already, and I keep on going up, but instead of continuing my wave, I suddenly restart from the bottom of the wave, and that means 0, 1. Okay, if I want to send instead 1, 1, I could do what I do for BPSK and suddenly change direction, like this. And if I want to say instead of 0, 0, 1, 0, if I was going up, well, I'll continue going up, but actually I'll jump directly to the top of the wave, which means that I will start from the top and go down, like this. So you see, we have 4 changes. One change to say 0, 0, you continue a wave as if nothing was there. One change is BPSK, right? You say you were going up, you suddenly go down. And the 2 other are intermediate changes where you say you were going up, you restart from the bottom. Or you were going up, well, you jump directly to the top of the wave. So that gives you 4 different possibilities, and of course, because you have 4 possibilities, you can represent 2 bits, because there are 4 combinations in 2 bits, and that gives you the ability in each click to represent the change of 2 bits, and that allows you to double the speed from what you had before. So if BPSK allows you 1 megabit per second, QPSK allows you to double. Now you are 2 megabit per second. So that's a lot better. Again, QPSK, just like BPSK, is used everywhere. You need to know how it works because you'll be very comfortable in many, many radio technologies. But still, in Wi-Fi, we are at 2 megabit per second. That is not a lot. How do we do better? Well, then we need to be a bit more intelligent or more complex.